In this question, again, we have a joint probability density function that belongs to two random variables, x and y. And both of these random variables are taking values between 0 and 1. So they are both taking values in the unit interval. Actually, this is not a general situation. In many of our examples that we have solved in the theoretical course, just for simplification purposes, we were defining the joint distribution within the unit intervals. However, generally speaking, just like any other random variable, these random variables as well can be defined in any interval. Okay, so this is a simple joint PDF, which is defined in the unit square. So both random variables are defined in the unit intervals, and the probability density function is a linear function of the input variables x and y. So it is equal to 2 minus x minus y. And elsewhere, the PDF is 0, which means these random variables cannot take any other value outside the unit intervals. So in the first part, it asks us to find the marginal probability density function and the marginal cumulative distribution function of random variable x. And then we can easily use the cumulative distribution function to compute the probability of capital X being less than or equal to 0.5. So basically, if we find the marginal PDF by integrating it as usual, we can compute the marginal CDF, then we can answer the questions. So before moving forward to the other parts and solve part A, let's just illustrate the joint probability density function, which can easily be illustrated. It is not asked in the question. However, we are still going to do it to understand the behavior of the probability density function. So it's minus x minus y. So it's three dimensions, just like this. When x and y are both equal to 0, the probability density function is equal to 2, as you can see. When x is 0 and y is also equal to 0, the height of the probability density function is equal to 2, of course. When x and y are equal to 1, as you can see in this corner, the PDF function becomes 0. And with respect to the other values in the unit interval, the function decreases in a linear form. And basically, this function forms a plane on the three-dimensional space. When you look at the picture here, you are basically seeing half of a square prism. So we have a square in the base, and this is a square prism. The shape is a square prism, and we are cutting it from this corner to this corner with a plane, and this is basically half of a square prism. And the total volume under this function, under this plane, is basically equal to 1. Why? Because it is half of the total volume of the square prism, and the square prism has the volume of 2. All right, so let's try to give answer to the first part. Our objective is to determine the marginal PDF of x. Remember, in order to determine the marginal PDF of x, we need to integrate the joint PDF over the other variable y. And for any value of x, y can take any value between 0 and 1. As you can see, the boundaries are not dependent on each other. Y can take any value between 0 and 1, independent of the possible values of x can take. And we will integrate the joint PDF with respect to y, and with respect to dy operator. If you integrate this function, you are going to get 2y minus xy minus y squared over 2. Plugging in the y values as 1 and 0 at the upper bound and the lower bound, you are basically calculating the marginal PDF of x, which is 3 over 2 minus x. Now, because x is also defined within the unit interval, this probability density function will be valid in the unit interval. And if we want to calculate the marginal cumulative distribution function, remember it represents the probability of random variable to be less than or equal to any arbitrary value x, which requires the integration of the PDF from minus infinity to that certain value. Since this certain value is represented x, we are changing the variable in the PDF and the integral operator to t. And since our random variable can never take any negative value. It is this integral is going to be calculated between 0 and x. Instead of minus infinity and x, we can start the lower bound of the integral from 0, because the PDF is basically equal to 0 in the negative region. And once we integrate that integrand, we will be calculating and plugging in the upper bound x and lower bound as 0. You will be getting the cumulative distribution function of random variable x, which can help us to calculate any probability defined in this form within 0-1 interval. So if somebody asks us the probability of our random variable to be less than or equal to 0.5, because 0.5 is within this interval, we can basically plug in that value in this function, and then we can calculate this probability as 5/8. Okay. Now, one thing you need to be careful here, as you can see, the possible values of these random variables x and y are defined within the unit interval in both random variables, and also the contribution of these random variables into the probability density function are the same. Okay, so both of these variables are subtracted from 2 in the probability density function, and the possible values these random variables can take are also the same, and the possible values that they can take, or the set of possible values that they can take, are not dependent on each other's values. So the contribution of both variables are the same into this function. Therefore, if somebody asks you the marginal PDF or the marginal CDF for random variable y, then you can easily answer they should also be the same as the marginal PDF of x and marginal CDF of x. Why? Because basically all of these operations will be done for y this time, and again you are going to get the same values. The probability density function of y will be 3/2 minus y, and the marginal cumulative distribution function of y will be 3y minus y squared over 2. So the same functions will be observed. Why? Again, telling you, because the contribution of both variables are the same into the function, and the boundaries are also the same and not dependent on each other. Now, the next thing that is being asked is to compute the expected value of x, then compute the variance of x. Now, how can we calculate the expected value of x? Since we have already computed the marginal PDF of x, we will multiply this marginal PDF with x itself, and this integrand will be integrated within the domain of that random variable. That random variable is supposed to take values between 0 and 1. Therefore, we integrate this integrand from 0 to 1. And when you multiply the PDF with x, you get 3x/2 minus x squared, integrated from 0 to 1. The integral calculated here as 3x²/4 minus x to the power 3/3. This is a simple integration of polynomials, and plugging in the upper bound and lower bound and subtracting the values will give you a 5/12. Therefore, we can say that the expected value of x here is 5/12. In fact, the expected value of y will also be the same, because the probability density function, the marginal PDF of y, is also the same. So that both the expected value of x and expected value of y are same, and they are both equal to 5/12. Now, in order to compute the variance of x, we are just going to compute the expected value of x squared as usual. Then we are going to plug in that expected value of x squared into the convenient variance formula. The expected value of the square of x is calculated by integrating the integrand x squared times the marginal PDF of x, again over the domain of our random variable between 0 and 1. And once this is integrated, you will get 1/4. Since expected value of x squared is equal to 1/4, you are just going to plug in that value here, and the square of the expectation will come from part B, which was 5/12. The expected value was 5/12. Squaring it will give you a 25/144. subtracting it from 1/4 will give you a 11/144, which is the variance of x. And again, the variance of y, the other random variable, would also be the same because the contribution of that variable into the probability density function is also the same.